How's it going?
Well, it's going better where you're at than where I'm at. We got 1.5 feet of snow on the ground,
Wow, that's a lot.
but that's okay. You get bored with all that sunshine in Florida, don't you?
Yeah, it's always great. Don't have to worry about money.
Same weather every day. Well, actually not. I visited my kids once in January, 4 years ago when it got down to freezing, and none of the hotels have heat. So
Oh, really?
yeah, so I spent a week in Boca Raton with freezing temperatures and no heat.
It's a,
The houses almost have heat, but most of the hotels and motels don't.
oh, that's weird.
Yeah. So what are we doing today?
Um, today we're doing like a graphing. 1 second. I'll email it to you so you can see it.
Okay.
Inverse functions.
Okay. Solving for inverse functions tends to be pretty algebraic, so we can do those, but graphing them is, actually graphing of inverse functions is very, very straightforward. Instead of reflecting over the x-axis or the y-axis, you reflect over the line y equal x. That's the
Yeah,
graph of the inverse.
I sent it.
I don't even need this other one, right?
No, that just comes with it automatically for some reason.
Yeah, but I can still read the file without it. Yeah, it looks like I can. All right. Graph each function using the graphing calculator. All right, let's use Wolfram Alpha. Have I talked to you about Wolfram Alpha before?
Mm-mm.
It's a great,
No.
great website. In fact, let me copy and paste it into the GoToMeeting thing.
Okay.
See it in the chat window?
Yes.
You could actually click on that and it'll open up in your browser and then you can save it. And
Okay.
we'll do the work on mine because I'm familiar with it, but it's a much better calculator than whatever other calculator you're using. Uh, and I'll tell you why, is it tells you what you put in. In other words, if I want to put in 4x squared plus 2, I'll put in 4x raised to the 2 plus 2. Well, on your graphing calculator, it doesn't tell you what you put in. It just gives you whatever the graph is, right?
Yes.
But this, I can tell I put it in exactly right. In other words, sometimes, you end up with 6 to 8 parentheses in the expression, and it's awful difficult to know whether you've put it in correctly. So Wolfram Alpha is beautiful in that regards. It also gives you a close-in and a zoomed-out double graph of it. Notice the x-axis here is 0.5 and 1. It's the y-axis that's changed. Yeah, they've made the y-axis.
Mm-hmm.
No, the x-axis has changed a little bit. So there's the graph of it. The question says, sketch the graph on your paper. Okay. Never seen instructions quite like that, but where it says graph it on the calculator and then graph it on your paper.
Yeah.
And then apply the horizontal line test. Does the horizontal line test pass on this graph?
It touches it at 2 points.
So,
Or no, it doesn't touch
so
it.
that means
So
it fails.
it's a failure.
The vertical line test passes I can pass any vertical line through that graph that I want, and it only hits it at 1 point. But horizontal lines hit it at 2 points. So that means it's 1-to-1 or not 1-to-1?
Wait, explain 1-to-1.
Not 1-to-1. 1-to-1 means it has to pass both the vertical and the horizontal line test.
Okay, I don't have to know what vertical is on this one yet.
Well, here, let me draw a function that passes both.
Okay.
If I draw the function y equals x cubed, notice that I can pass a vertical line through that or a horizontal line. Either one passes it. So that's 1-to-1. And what 1-to-1 means is that it does have an inverse. Has to be 1-to-1 in order to have an inverse. Or has to be restricted. Well, the function they gave us, which graphed like this, that's not 1-to-1. But if I tried to graph its inverse would look like this. In other words, if I take this original function and I reflect it over the line y equal x, comes out to be my horizontal parabola.
Okay.
And the horizontal parabola is not a function because it fails the vertical line test. So if you take a function and graphically get its inverse, it will not be a function if the original one was not 1-to-1. If I take my x cubed, I can reflect that over that imaginary dotted line, and it reflects just fine. Reflects into something that looks like that, which is still a function. It's 1-to-1. So when you have 1-to-1, you can get an inverse on it. Now, this actually does have an inverse. It says state if the function's inverse is also a function. Well, with that parabola, the inverse was not a function, right? It was still a horizontal parabola, but that fails the vertical line test. So the inverse is not a function.
Okay.
Okay. Number 2. X plus 4 over x minus 2. X plus 4 divided by x minus 2. I'm going to intentionally make a mistake so you can see. Notice what it did. Because I didn't put in the parentheses. I need parentheses there for the numerator. And I also need parentheses for the denominator. Now, it'll give me the right function and it'll tell me what function I put in there. Does that function pass the vertical line test?
Yes.
Horizontal?
Yes.
So it is 1-to-1. It would have an inverse, and the inverse function would also be a function. And notice they don't ask you to actually come up with the inverse. Is that on purpose? Have you not had that yet?
Yeah, we do come up with the inverse usually, actually.
Let's do it on this one, because this is a little bit of a tricky one here. If I have y, let me change back to red. I have y equals x plus 4 over x minus 2. Is that it? How do I find the inverse? 2 steps.
But you have to make the x's into y.
Switch the variables and then solve for y. Those are the 2 steps. Always. Switch the variables. There's step 1. And then step 2 is always the harder one. Now solve for y. And solving for y here, do you know how to do it? It can be a little tricky.
No, I don't.
Well, algebra 2, probably. Multiply both sides by the denominator. So we would have x times y minus 2 equals y plus 4. Distribute. So now we have xy minus 2x equals y plus 4. And this is the tricky step. What's the step here? The next.
Subtract.
Actually, the next step is to gather every term that has y in it on one side of the equation and everything else on the other. So xy minus y equals 2x plus 4. Okay?
Okay.
Now, factor out the y. So you're left with x minus 1. And now divide both sides by the coefficient x minus 1, and you've solved for y.
Okay.
That's the inverse. If I were to graph that function right there on Wolfram Alpha, it would be this function reflected over the line y equal x. That's all it would be.
Okay.
Okay. And some inverses can be particularly tricky to solve for. If you end up with a quadratic, in other words, we don't have any quadratics here, but if I started out with y equal x squared minus x minus 2, or something like that, that's going to be really difficult to solve, because once you switch the variables, solving for y is no longer easy. It's quite difficult, in fact. All right. 3x minus 1. Let's skip plotting that in the calculator and just graph it on our paper. 3x minus 1 goes through there, has a slope of 3. That's y equals 3x minus 1. Is that 1 to 1?
Yes.
So it has an inverse.
Correct.
And, well, I keep making that mistake. I keep thinking that if it's not 1 to 1, it doesn't have an inverse. According to the paper, it has an inverse. The question is the inverse function a function? And that, in this case, we can say that the inverse is going to be a function because the original function is 1 to 1.
Yeah, I got x plus 1 over 3 equals y.
Right. Yeah, this one's really easy to solve. Once you switch the variables, solving for y becomes easy. That last one was a little more difficult. But, okay. This one here.
5, I don't understand exactly.
Well, okay, let's talk about 5, and then we'll go back and look at 4. 5 is y equals 6. What's that look like?
This is a straight line and
vertical
6.
or horizontal?
It's a horizontal at the 6y.
Okay. Does that pass the vertical line test?
Yes.
Does it pass the horizontal?
No.
No, not if it's a true, the way I drew it, it might, but if it's a true horizontal line, then no, because when you get the horizontal line right on top of it, it's going to hit a bunch of points at the same time.
True.
It does not pass the horizontal line test, meaning the inverse function is not a function. And the inverse of this is going to be a vertical line, and a vertical line is not a function. It doesn't pass the vertical line test.
Sure.
Okay.
Okay.
Let's look at number 4, 3x cubed minus 6. Well, let me just draw that. I don't need Wolfram Alpha for that either. In other words, all this is a translation of the elementary function y equal x cubed, right? Shifted down by 6 units and stretched by 3 units, vertically stretched. So it's going to go through this point right here instead of the 0, 0. It's going to be vertically stretched, so it's going to look something like that. Now, I didn't draw the end of it very good. Mainly I didn't draw it very good because it's wouldn't pass the vertical line test the way I drew it. Is that 1-to-1?
Yes.
So its inverse is or is not a function?
I think it is.
Yes. If the original function is 1-to-1, then the inverse is always a function. So as long as the original function passes both the vertical and the horizontal line test, then the original function is 1-to-1. Well, you might ask, how do they have inverse trig functions? Because if I take the sine curve, that clearly passes the vertical line test, but it does not pass the horizontal line test. So I can talk about the inverse sine, but it's only a function if I restrict the original function. So the way they actually are able to use inverse trig functions is they restrict the original function between those 2 points. In other words, the sine curve goes on and on forever, right?
Yes.
So by restricting the domain from minus pi over 2 to plus pi over 2, in other words, just this part of it, now all of a sudden I'm looking at something that is 1-to-1. And I can take the inverse of that, and the inverse will be a function. And it's very important that it be functions. It's not immaterial as to whether it's a function or not. If my inverse is not a function, then it doesn't work really well for doing anything. It only works well mathematically if it's a function. So I would prefer all my inverses to be functions, but sometimes you have to restrict the domain of the original function in order to make that happen. With sine, they restrict the domain from minus pi over 2 to pi over 2. But notice that wouldn't work very well with cosine, because cosine looks like this. So if I restrict it from minus pi over 2 to pi over 2, I don't have something that's 1-to-1. So with cosine, they restrict it from 0 to pi. In other words, from there to there. So cosine is always restricted to the first and second quadrants when you're talking about the inverse, and sine is always restricted to the first and fourth quadrants when you're talking about its inverse.
Okay.
All right, here we have some where we have to find the inverse. Okay. Find it and graph it. Well, let's find it first. And it always makes a little more sense to write these as y instead of f of x, merely because the rule is switch the variables and solve for y. What's the next line?
Would it be +1?
First of all, switch the variables.
So then it would be 1/5 and y
Start from the left.
equals -1, 1/5y.
In other words, the first step is really quite simple. There's never any problem with switching the variables. Now, what's the next line if I'm trying to solve for y?
Then it would be +1. Would we multiply everything by 5?
By -5. If we multiply by -5, we'll leave y all by itself, which is what we're trying to do. So
Okay.
-5 times x plus 1 equals y. So if I want to switch sides and distribute, there's the inverse. And that's a function also.
Okay.
Okay. And as far as graphing it, if you can graph the original function, then the way to graph the inverse is to just reflect it over y equal x. Now, that's sometimes easier said than done visually. It's not always that easy to reflect it over that line. But in other words, I always have a little difficulty when I'm dealing with y equal x cubed. And I have to reflect that over this line. Basically, what you do is you take every point, like right there, and you put it on the other side of the line. So to reflect it, I'm going to draw it like this. And there's my inverse. Or, in this case, I can graph the first one quite easily. That's linear, right? In other words, that's y equal mx plus b. Slope's -1/5. Y-intercept is -1. So that's just a straight line with a negative slope, something like that. That's this function here, number 6. And after I've calculated its inverse, now it's still a straight line, still a negative slope, but a steeper, and its inverse looks something like that. And you will find that these two red lines here that kind of make an X, one of them is a reflection over that y equal x right there of the other. How about 7? Now, these are a little harder because these aren't linear. Notice this is hyperbolic. So the graphing of this might be a little tougher. But I know what hyperbolic functions look like. They look like this, right?
Yes.
And as all this is I know that there's a vertical asymptote at x equal 1, because I can never have division by 0. There's a horizontal asymptote at y equals 0. And now I'm going to graph it. I'm going to put my hyperbola in the upper right and the lower left quadrants. So that's how I would graph that function there. Now let's solve for its inverse. I'll leave this up over here. I'll work in blue for the inverse. So the first thing, switch the variables. Solve for y. How do I solve for y?
Could I multiply the bottom by 1?
Always multiply by the denominator, the whole thing. In other words, let's multiply by y minus 1.
Okay.
If I multiply by y minus 1, it gets rid of that denominator. And that's always a good thing. Denominators only make equations harder to solve. Okay, well now that cancels with that. Now I distribute over here, and I get yx minus x equals 1. Add x to both sides. Yx equals 1 plus x. Divide both sides by x. There's your inverse. 1 plus x over x. Now,
Okay.
graphing that, I don't know how to graph that. In other words, I don't automatically know how to graph it. You can always graph any graph by making a table, but in terms of an elementary function, I'm not sure I know how to graph that. Actually, I do. But the one thing we know is that since this is an inverse to this, then its graph has to be a reflection about this line right here. So if I reflect the original solid red graph over that blue line, I end up with my inverse function, which is this one. Now that inverse function is actually 1 over x plus 1. Well, I know how to graph that. That's hyperbolic. That's everything shifted up by 1.
Okay.
And that's what it would look like. If I reflected the red over the blue, it's going to be hyperbolic still, only it's going to go through this point right here. In other words, it's going to have asymptote at 0 instead of 1, and so forth and so on. Actually, that's probably coming up for you. Yeah, because you're just starting the pre-calc, so you've been studying domain and range and all of that good stuff.
Yep.
The other thing about inverse functions is if you have a function that's the inverse of another function, is all you can just switch the x and y values. Always.
Okay.
Now, all of these are, I don't see any tough ones here. The only thing that would make it tough if it was a quadratic. Cubics, there's no problem, because when you take the cube root of a number, you don't get plus or minus. You get either plus or minus. But when you have a quadratic and you take the square root of it, you get plus or minus, automatically not a function. So that's why all of these problems, they're either cubics, or they're linear, or they're hyperbolic, but notice none of them are quadratic. And there is a very special way you would have to solve quadratics that's extremely confusing. So hopefully you won't have to do any of those, but if you get some, let me know. I know how to solve them.
Okay.
I'm looking at number 8. That would be x minus 1 divided by minus 2, the cube root of all of that. Yeah, there's only, it's an inverse function. All right, Taylor, I will let you go. I have a 4:30 I got to get to.
Okay, sounds good. Thank you.
Have a good one. Bye-bye.
Thank you for your time.